Okay, so continuing our look at probability, what we're going to do is we're going to look at complements, the word and the word or. Now this is different from the title that you're going to see when you do this in the book, but to me, these are the words that have meaning. And we're going to work with that and see what happens. In the book, they call this multiplication and addition. But to me, it's more important to know when you need to multiply and when you need to add or subtract and what's going on. And that's given more by these words, these keywords. So those are the ones you need to focus on. So that's why I've used them in the title to make sure that that's your focus. Okay? But the first thing we're going to talk about is we're going to talk about complements. So let's say that the probability of an event is A. If A is the event, then the complement or complementary event, I would just say complement if I were you, is not A. Right? So complement is not the event you want. Instead, that's supposed to be a bracket, it's everything else. Okay? So for example, if I want a 6, that's the event I want, right? But is 6 the only number on the die? How many other numbers are there on the die? 5 others, right? So those 5 numbers are the complement to getting a 6. And I know it seems odd because you don't really think of a complement and not be going together, right? Okay. But they complement each other because they're said to complement each other because of this. This is why they're called complements. If you add the event and not the event, they're going to give you a probability of what? 1, which is the same as, remember that 1 is the same as 100%. Keep that in mind too, and just for the notes. Yes. And that's the notation for complement. Yeah, we'll talk about that in just a second. So, this is the event. This is the notation for the complement. Okay? And it's often, if you see the little apostrophe, A apostrophe is often read as A prime. Don't ask me why, because I don't know. But anytime you see that little apostrophe, it's often read as prime, A prime. Yes? Okay. That's what you're looking at, yes. So, for example, if the probability of A is getting a 6, okay, then the complement of that, or A prime, is not getting a 6. Is that better? Right? So the event means getting what you want. A prime would mean not getting what you want. Okay? Because if you roll a die, are you always going to get a 6? Nope. You might get something else. You're more than likely going to get something else, right? So, those are the complement of them. Yes? Well, absolutely. Or easier. Okay? All right? So, and I'll write that down right now. If you know, and that's what this formula is telling us here. If you know the probability of an event, okay, simply subtract that number. Everybody remembers the hashtag really means number. I don't know. It's been hijacked. Subtract that number, so you can write number if you want to, from 1 to get its complement. Okay? So, you could go back and just find the other probability, the probability of everything else. But it's easier just to find the probability of what you want and subtract that from what number? 1. Because if you add these two, if you add them together, they're always going to give you 1. Right? And so this is an identity. If P of A plus P of A prime equals 1, if those two added together give you 1, then you can always find the other by subtracting. Right? You've done this with numbers forever and ever and ever. Okay? Nope, that's not going to work. So let me try something else. Okay, let's see if it gives me a new page. Yeah, here we go. So, if I know that 6 plus 5 equals 11, right? Then 11 minus 6 has to be what? 5. Do you see, right? If you change it to a subtraction, then you just take the difference, in this case, the sum, minus one of the add-ins has to give you the other one. Okay? So, if the probability of A plus the probability of not A equals 1, then I can find the probability of not A by simply taking 1 minus the probability of A. Okay? So if I know the probability of rolling a 6, which I do know, it's 1 out of 6, right? Then I can take 1 minus 1 over 6, which gives me 5 out of 6. And this is where slipping into decimals might be your friend. But you can use your calculator to do fractions. And do you know how to change it so that it gives you a fraction back as an answer instead of decimal? If not, figure it out. And then, because it'll make your life a lot easier. Because your calculator is either going to return a decimal or it's going to return a fraction, right? And you can choose between the two.
So this would be theoretical probability instead of experimental.
You could do that, yeah, because, you could do this with some experimental probability. You couldn't do it with a survey. Well, yeah, you can. You can do it with any probability, as a matter of fact. 1 minus. Because every answer is always going to give you what percent? 100%, which is the same as 1. So, yeah, any probability will have a complement. So, if 30% of the people use Dove soap, that means that 70% of them don't, right? So you see the complement there? Because both of them added together give you 100% or 1. Okay? And that's why they're complements. It's hard to get your head around complements when they use the word not. That doesn't make sense. But the two added together make everything. Mm-hmm.
So if you were writing out what was if you were doing the rolling a 6,
okay.
How would you write the A? Would you write it as what the
So the probability of getting a 6 is what? 1 out of 6. The probability of 6 prime, not getting a 6, 5 out of 6. Okay, it is another way of taking a shortcut, so you don't have to write out all, because otherwise you'd have to write the probability of what? 1, 2, 3, 4, 5. Okay? So instead, you can just write 6 prime. Now, in some textbooks, you might see the apostrophe on the P. It means the same thing. But here they're putting it inside with the P.
Is that just like saying it's complement?
It just means complement. I have no idea why it's called prime. Maybe I should look that up one of these days so I can answer your questions. Yes? Everybody always asks.
If you're ever doing like a really big question and a test and you have to write that, will they know what it means?
Yep. And you're going to have to write it. On the probability exam, the NCAA probability exam, they're going to ask you to find the complement. And you're going to have to write probability of A prime. Yep. You're going to have to use the proper notation. Okay? All right? It's the same as saying not getting in it whatever you want. And getting what you want and not getting what you want is 100% of what you can, right? You either get it or you don't get it. That's every option. There's nothing else left. And that's why they're complements. Okay? All right. So, here's an example. The probability of a tennis player getting her first serve is 0.65. What's the probability of her missing her first serve then? Yeah, 0.35, right? Those two numbers just have to add up to 1. So just take 1 minus the 0.65, and that'll tell you the answer. All right? It's a pretty simple concept, okay? But keep it simple. But it is new, right? Maybe. Study complements in any other probability class you should have done. Oh, wow, that surprises me. Okay? Good deal. All right. So, does every event have a complement?
Yes.
It can either happen or it can either what? Not happen, right? Doesn't matter what the event is. It can either happen or not happen. So, yeah, everything has a complement.
Unless it's totally certain, then would the complement be just 0?
The complement would be 0. 1 minus 1 is 0. Mm-hmm. Yeah. Okay. And 0, an impossible event has a complement too. If it's dead certain not to happen, the complement of that is 1 that it is certain to happen, right? Okay. So if you have a certain event, an impossible event, the probability that it is not going to happen is, there you go. Okay? All right. So here we go. And this is they call it the multiplication rule. I like to call it, and they even have it here, I like to call it the AND rule. Because you're not going to be thinking in terms of, they're not going to write the multiplication rule. They're going to write the word AND. So you need to know what happens in probability when you see the word AND. Okay? And so this is the AND rule. But what do you think you're going to do when you see AND? Multiply, exactly. So when you see the word AND, the probability of AND, the probability of A and B occurring is the same thing as saying the probability of A times the probability of B. You're simply going to find the probability of each event and multiply them together. Now notice, the AND is in the parentheses with the two things, right? This is not the probability of A and the probability of B. It's two different probabilities, right? So that's a little bit different. So make sure you watch out for the notation. Now, this rule applies as long as both events are independent of each other. Now, you've heard the word independent before, right? This is just a more formal way of using it. Independent means that it doesn't matter what else happens, okay? So, for example, let's say I flip a coin and I roll a die. Does what happens when I flip the coin affect what happens when I roll a die? No way. Those are independent events. Okay? So and some of them are very easy to determine. Some are a little less easy to determine. So we need a way to do it, and we'll learn that in a minute. Yes.
What does times do?
It just gives you the total probability, because it's the probability of both of them. Yeah. So let's look at an example, and let's show you.
So that finding the average.
Sorry?
So it's kind of like finding the average of all different probabilities that it makes.
Yeah, it's finding out the probability of two different things, of doing two different things. What would that probability be? So you've got two different independent things going on. What's the probability of that happening? Okay? All right? So let's look at this one, for example.
Sorry, could we spell it just a second? Because I didn't check it.
Do you want what I wrote or what's on there? Okay? You're going to have this too. So you can just go to these pages on Education Perfect. But yes, I have no problem scrolling. All right. Scrolling's easy. So a fair die is rolled. Okay? So that's one experiment, right? And a coin is flipped. That's a separate experiment. So you see what's going on here? We have two different experiments happening. We're going to perform them both. What is the probability of getting a 4 and a tails? Okay? Well, all I have to do is look first at the connecting word. I want a 4 or a tails, or a 4 and a tails. And always is the magic word in probability that means what operation? Multiply. Okay? So all I need to do is find each probability and then multiply those probabilities together. So the probability of rolling a 4, right? There's 1 4 out of 6 numbers, so that's 1 out of 6 or 1/6, right? The probability of getting a tails, there's either heads or tails. Tails is only 1 out of how many total possibilities? 2. And since it's an and statement, that means a multiplication. So all I'm going to do is multiply those two things together, which is going to give me 1/12. Okay? So watch out for those connecting words, and. Now, we could also solve that same question by drawing the sample space. And I'm going to make you draw the sample space for this. And you're not going to like it because it's a lot to write. But you need to draw it and actually do it, physically do it, because you're going to have to draw sample spaces at some point, and it's really important skill. It's very easy, but it's a really important skill. And all you're doing for a sample space, remember, the sample space is simply a representation of everything that can possibly happen. Okay? So, here we go. Let's write a sample space. So what we want is the probability, right, of rolling a number on a die and the probability of heads or tails on a, right? We want to write everything that can happen. Okay? So let's just think about that. So we want every number represented, and we want heads and tails, maybe. Sorry, where'd I get the D from? I don't know what I'm doing. So, die, I guess. Probability of heads or tails. So, let's say I could get a heads and a 1. Could I have started with tails? Sure, who cares? I could get a heads and a what? 2. I could get a heads and a 3. I could get a heads and a 4. I can get a heads and a 5. Or I can get a heads and a 6. I told you won't like it. You might be asked to ask for a sample space. Yes. This is a small one. This is a very small one. It's one of the smallest ones you can do. All right? Now, that is every possibility with heads, right? Don't bounce around when you're doing these. Write them all. Heads in 1, heads in 2, heads in 3, heads in 4, etc. Do them in order, or you will miss some. Okay? Yes?
Sorry, so what's this for?
This is just writing the sample space. Okay? What we're doing is writing the sample space for this particular group, for this particular experiment. I'm right, and sample space means every possible outcome. Okay? Now, if I don't get a heads, I'm going to get a what? Tails. So the next list is going to be tails in a 1, tails in a 2, tails in a 3, tails in a 4, tails in a 5, tails and a 6. Okay? Now, if that's too much to write, y'all are lazier than me. I can't believe it. That's pretty good. Yes? You could write it in as a grid. I like to write them up and down like that because I like to keep all the heads together and I like to do them in numerical order. You can write it as a grid. They did it as a grid in the other one. Either way, it's fine. Organization is up to you. How you organize it is up to you. Okay? Sorry, yeah, I changed it, didn't I? So they went across, I went up and down. Doesn't matter as long as you get them all. Now, what we can do with the sample space is we can now find the probability of, what were we looking for? 6 and a tails or what? I don't even remember.
4 and tails.
4 and a tails. Thank you. 4 and tails. Because all I have to do is go on my sample space and find the one that matches. There it is, right there. Are there any more that have a tails and a 4? Nope, that's it. So it's 1, and how many different outcomes were there? So there's your probability. Okay? It is very much work. That's why we don't do probability using sample spaces. But it's important, especially for what we're about to learn, it's important that you be able to do it. Now, most of the time they'll give you a sample space, but a small sample space like this, they might ask you to draw. Okay? So be prepared to be able to do it. It's not hard, is it? No. It's just, right? And if you can draw a successful sample space and you have a really complicated probability problem, sometimes if you draw the sample space, you can answer the question easier than if you're trying to do it with the math. All right? We had some of those on the exam. Yes?
Sam, can you explain the headings, the P?
Yeah, P.
Oh, the P of whatever the number is and the probability of a heads or tails. Those are the two different things we can get. So the probability of a 1, 2, 3, 4, 5, 6, and the probability of heads or tails. Sorry, how's that? Is that better? Okay. Because those are the options. What are you going to get when you roll a die? A 1, 2, 3. So the sample space is the probability of everything we could that could possibly happen.
I thought that it was the headings of the.
Yeah, no. I'm sorry. No, those are just the two probabilities. Sorry.
Okay.
Yeah. No, please ask those questions because my job is here. Somebody else have a question? Somebody else had their hand up? No.
Oh yeah, that was the same question.
Okay, so they're not headings. They're just the two probabilities that we're listing.
Cool.
There you go. Yes.
This isn't really about that, but it is about maths. Do we have to get the 10 numeracy credits this year?
Get the what now?
You only need level 1 credits to pass UE
Oh, okay. So,
for math, but for English you need the level 2 ones.
okay.
Yeah. Okay, guys. So do you see that you can get this from the sample space? Now, what did we do when we did just the math to get this? What probability did we get? 1 out of 12. When we multiplied them together, right? And because the two probabilities were the same, we know that these events are independent. Because the probability is the same if you do the math or the sample space. And for now, that's our only method for knowing that two events are independent.
What do you mean by the probability system?
Okay, what did I get when I listed it out? What's the probability of getting a tails and a 4? Okay, now, let's see.
Oh, wait, so when you put
What did I get when I'm? Oh crud! Now I'm don't know where. What did I get when I did the multiplication? So they're the same, right? And that tells us that the events were independent.
so you have to prove it both ways.
Yeah, you have to prove it some way, right? And that's one method of proving it. Okay? Now, see if I can get back to where I am. This recording may be a little messy. Okay. All right. So, right? Here's just a simple one. That. There we go. Here's just a simple one. The probability that a person has curly hair and is left-handed. They give you the probabilities, right? But where is my key word here? And. There you go. Which means I'm just simply going to take the two probabilities they gave me and what? Multiply them together. You bet. Okay? So, and that gives you the probability for that particular problem. Right? Now, there are times when you can't use the multiplication rule. And always means multiply, but occasionally the rule fails. That rule fails. And it happens when two events are not independent. Okay? And a lot of it has to do with the wording, the way things are worded. So this is where probability becomes a little troublesome for some students, for most students. Finding a basic probability is not usually a difficult situation. Multiplying two probabilities together is not a difficult situation. Knowing when you can, however, throws a wrinkle in. And that's why we looked at how to find it with the multiplication rule and how to use the sample space. Because if those two probabilities are different, if you had gotten a different number for those two probabilities, then you know that they're not independent. And later we're going to learn a formula for this. But for right now, we're going to use the sample space as proof. But later, we'll develop a formula behind it. But for now, we're going to use the sample space. But be happy. They drew the sample space for you. So 2 dice are rolled, right? So I got 2 different dice. I'm going to roll them, right? Find the probability of getting a total of 7 on the 2 dice and rolling a 3 on either die. So I want 2 probabilities. What are my probabilities? Probability of a sum of 7. Not the probability of 7, right? A total or a sum of 7. Which means I'm doing what to the 2 numbers I roll? Adding them together. Whoops. I didn't mean to close that parentheses. And a 3 on either die.
So it's essentially asking you for 3 and 4. Well, you can do. So you can do a 5 or a 2 though. There's different probabilities.
Be careful. So they're being very specific, aren't they? So it's got to be 3 and 4. Or what?
4 and 3.
4 and 3. The order is not going to make any difference here. Okay? But let's see what happens here when we look at this. Okay? So let's separate them, because remember, it should be the probability of a sum of 7 times the probability of a 3 on either die. So we could have written that as probability of 3. It's the same thing. Okay? We roll 2 die. How many ways are there to get a 7? You can get a 1 and a 6. So, okay. Think carefully. Be careful of all the different things, of all the different ways you can get a 6. So, let's look at the sample space. Let me scroll up. So, the probability of a total of 7. You can have a 1 and a 6. 2 and a 5 would do it. 3 and 4. 4 and 3, right? You have to think of because it's 2 different die, so the order, right, is still the same total. 5 and a 2 and a 6 and a 1. So that's 6 different outcomes. How many different outcomes does it say there are if you do that?
36.
36. It says so right there up there at the top, right? There are 36 different outcomes and 6 of them. So 6 out of 36 is probability of 1/6. Right? Do you agree? Reducing it? Okay. Now, the probability to get a 3 on either die. That's every possible combination way of getting a 3. So do you see how having your sample space here is helpful? Because you can just look every space where there's a 3. So all of those, that one, and that one, all of those will work. Notice how neatly that came out, straight up and down and straight across? In a sample space, an organized sample space, that'll always happen. Okay? How many is that? 11. Out of how many total?
36.
Will that reduce? No. So the first one we got, when we did it with the sample space, the probability of all that happening was 11 out of 36. When we did it by the math, the multiplication rule, the probability was what? Okay, so those are our probabilities, right? Now, okay, so that's the 2 probabilities we're going to do. So probability of getting a, what was it? Sum of 7. This is probability of 3 on either die. Okay, let's do the math. 11 over 36 times, oops, y'all know that the dot means multiplication. Are y'all okay if I slip into it occasionally? Because I've never used the x for multiplication because y'all are algebra level students. And so x is confusing. So 11 over 36 times 1 over 6. What do we get? You can give me a decimal. Come on, I told y'all have to do the math. Remember. So multiply those together because it's the probability of this and the probability of that. Multiply. Sorry?
66 over 1,200.
Okay. But yeah, because it's reduced. Just give me a decimal.
0.05.
1. And then it keeps on going? Okay? So some ugly decimal. Okay? Doesn't come out even. That's fine. Now, let's do it using just the sample space. Okay? All I'm going to do is I'm going to choose the ones that give me a total of 7 and, okay, probability of 7 and sum of 7, I'm sorry, keep writing 7, and the probability that you get at least 1 3. Okay? Well, it's got to be a 3 and add up to 7. The only way to do that is if it's a 3 first, then a 4, or a what? 4 first, then a 3. So how many pieces of the sample space that work? 2 out of how many?
36.
Which is, turn that into a decimal for me, please. Somebody? Because I did the other one as a decimal. I want this.
Oh, wait, yeah, no,
0.05.
0.5 what?
0.055555.
Oh, 5 repeating?
And then there's a 6.
because they run.
Okay, you rounded it to, okay. What did I get before?
059. 051.
Blah, 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 blah.
But there was another 0 before that. It was 0.9. 0.509. And then a bunch of others.
Okay, so 0.509.
5. It was 0.05.
Who cares? All right. Look at this probability and look at this probability. What do you notice about the 2 probabilities?
One is bigger than the other.
Yeah, they're not the same. The probabilities are not the same using both methods. Now, we got this one using the multiplication rule. We got this one by looking at the actual things that can happen. Which one do you think is probably the right one then? If we have to reject one and keep the other, which one do you think you would keep?
Sample space.
You bet. The one from the sample space where I actually physically looked at everything that could happen and chose the 2. So that tells us that in this particular case, the multiplication rule fails. Which tells me, if it fails, that those 2 events are not independent. In other words, what happened on the first roll affects what happens on the second roll. Now, we can do this logically. We could have gotten that. We could have understood that logically in the first place. Because think about it. What number do you have to get on one of the die? 3. Well, if the first number is a 3, the second number can only be a what?
4.
So if it can only be a 4, does that mean you can get anything you want? Therefore, the events weren't independent. If the first number was a 4, if the second number was a 3, the first number has to be a what? 4. Anytime you have one of those absolutes like that, if this, then that, then the events are not independent. Okay? So you could have done it logically to see that they're independent too. Okay? Now, so can you always use the multiplication rule? No. Most of the time, yes, but not if the events are not independent. So if you know you have to get an exact pattern, okay, or something about it changes, then you know you can't. But if you do the probability both ways and you don't get the same answer, you know that they're not independent and the multiplication rule fails. And then later, the later one, guys, is going to be on the assessment. There's a formula for it. Okay? And so the one that you have to know for the assessment is the formula, but it's going to come later. Don't worry about it right now. Okay? Yeah. We'll only do the practice and then you'll have the external later. Yeah. Okay. By that time you'll be okay. So here we go. There they give you the things that the multiplication rule product and the other product from the other one from the other. So they're not independent because they got different results. Okay? So, a couple of different ways of finding out if events are independent. But if you think about it, logic would have told us that these are not independent because if I get a 3 first, I have to get a 4 next. That's not an independent event. I have to get something, right? I have to get a very specific thing. If it's independent, that means I could get what? Anything. Yes?
Is the words that are common to both in multiplication rule, are those like specific sort of phrasing that we actually use in the exam?
Okay, I'm confused by your question.
Like, if you're gonna, when you say present your answer, do you have to say, like, the total outcomes that are common to both, like that specific?
You mean when you're listing these things like they did, that list probability 3 on either die, that kind of thing?
Yeah, like in your answers. Like,
No.
It's like the one that
No, in your answer, just the number you get is your answer. So you're talking about, do you have to list all this stuff?
No, the words that are highlighted.
Oh, do you have to say that in your answer? I see what you mean. I see. How do you phrase your answer? No, they're just making. All right. If you'll see, blue is a definition. This one is kind of that blue-green color. That's just an emphasis, right? So just saying the numbers that are common to both. Okay. All right. And again, red just means the emphasis. It's just emphasis. I get it. Sorry. Sometimes my little brain. Okay. All right. Another rule for or. The rule for or, the word, and so it's the or rule. Or is a different operation. Or is the addition rule. So instead of multiplying them, if you get or, you're going to take the probability of the first one and then add the probability of the second one. So if you see the word or, that always means that you're going to be adding the two probabilities together. Okay? So and, what? Multiply as long as the events are independent. Or means add. Okay? Now, just finding simple probabilities using the or rule. Find the probability of selecting a 4 or an ace from a deck of cards. Okay, 4 or an ace. How many, do you know decks of cards? There are 52 cards, right? And there are four of each number, right? So 4 out of 52 fours, right? So if you look at it, there are 4 fours out of a deck of 52 cards. Yeah? And an ace. How many aces are there? 4 out of how many cards? 52. So the probability of or means I'm simply going to take those two probabilities and add them together, which is really nice here because they have a common denominator already. So you just add the top numbers, the numerators. So that gives me 8 out of 52, which of course I would not leave as 8 out of 52 like they did, the slackers. What's wrong with that? It'll reduce, and you should reduce it, right? I wouldn't reduce them. I would like 4 over 52 would have reduced. Okay, 2 over 13? There you go. Okay? So you see they're bouncing all over this. All right, so you see the addition rule? Let's look at another one.
Oh, can you back just for a second?
I can. Oops. Well, I thought I could. Come on. Okay.
Oh, wait.
Oh, I skipped okay. I skipped something anyway on that that I need to show you. This rule applies as long as the events cannot both occur at the same time. Okay? So in other words, we wanted a 4 and an ace. Can a 4 be an ace? So they can't occur at the same time. But what if it said I want a 4 or a black card? Can a 4 be a black card?
Yes. Only twice though.
Then we're going to have to take out the part of the probability. We'll learn how to deal with that. Okay? So you've got to make sure that they can't both occur at the same time. Otherwise, it involves another step. Imagine that. Okay? Complicates matters a little bit. Okay? Good job. So let's look at this one. A music school has 80 students. So 80 is our total number of students, right? So it's going to be the denominator of whatever fraction we get. 80 students. They each have the option of learning one of the following instruments. They can do keyboard, guitar, singing, and here's my keyword. What is it? Or drums, right? Okay, so we've got an or situation here. The numbers of students learning each instrument are given in the following table. If it's selected at random, what is the probability they learn keyboard or drums, right? So you see they give us here, go ahead and move this up. They give us here the probability of learning a keyboard. There were 25 out of the 80. Probability of learning the drums, 15 out of 80. So we have an or statement, which means we're going to use what operation? Addition. So 25 over 80 plus 15 over 80 gives 40 out of 80, which they reduce to 1/2. Good for them. Okay? Simple addition. Are keyboards the same as drums?
No.
So you know that they're not going to, they don't overlap. Okay? They can't happen together.
Can you go back up to the previous one, just the English? Like after that, like the one before that.
The screen before that?
Yes.
The working out.
The ace.
Okay, you bet.
That.
There you go. Sure, you bet. Also remember that all of you have access to Education Perfect, so you can look at any of these slides later. Then I'll show you where they are when I tell you about your homework anyway. Y'all are used to it, but I just want to remind you if you haven't used it in a while. Okay? So and that's one reason I use the Education Perfect for the lectures is because you have everything that you saw. So not only do you have the recording, you have everything that they gave you too. Everything I write. So take screenshots. Mm-hmm.
So does it do your voice as well? Yeah.
Yep. You betcha. So you'll be good and bored if you do listen to it a little bit. Okay, here we go. The addition rule should not be used, so there's always an exception, should not be used when both events can occur at the same time. Let's look at an example of this. Find the probability of selecting a black card or a 4 from a pack of cards. Okay? we know that these two things are overlapping if we just ask ourselves the question. If we have a black card, can that black card also be a 4? So we know we have overlapping situations, right? Therefore, we cannot use the addition rule. Now later we're going to learn a formula that will allow us to use the addition rule. Okay? But for now, it just says they're just going to give us the sample space and show us why that can't happen. Okay?
Was that just one?
All right?
You know, for that other one we did about the 4 and the aces, are they overlapping as well then?
No, because a 4 can't also be an ace, right? Okay? So a 4 can be black. So, overlapping. Can you have an ace? Can an ace be a club?
Yes.
Overlapping. Can an ace be a king? Not overlapping. Yeah. Okay. All right. And some of you aren't used to cards. Okay. So here we go. So there are 28 outcomes. So using the addition rule, you get one probability. And then if you look at the probability from the sample space, it's counting stuff twice. Right? So be careful if they're overlapping. Okay. So what if I had 3 and a diamond? Overlapping?
Yes.
You bet. Okay. Red card or a black card? No. So addition rule is fine. Okay? So watch out for when they overlap, if they overlap. Let's look at another example using complementary events. Adults? Where the heck did I come up with that? I don't know where that came from. Events and the multiplication and addition rules. Sometimes I really worry about me. Okay. The colors of the car and the car park are counted, and the proportion of each is shown in the table below. So this time they're giving us our probabilities as percentages, which is one of the 3 ways of writing them. Perfect. If a car is selected at random from the car park, what is the probability that that car is silver? 32%. Good. Okay. We're just reading straight from the chart. What is the probability that it's not silver?
68%.
You bet. It's 100%, which is the same as 1, minus 32%, which is 68%.
Do we have to show working like that?
Unless it asks you, be careful though, you know NCA. If it says describe, you better show the working. Okay? All right? It's not going to kill you to show the working, but you don't have to. Okay? What is the probability the car is white or black?
60.
Probability of white is 20%. Probability of white is 20%. Plus the probability of black is 16%. This gives you 36%. What is the complement of that?
16.
Right, just everything else, right? Subtract it from 100%. 1 and 100% mean exactly the same thing, right? Keep that in your heads. 1 and 100% are exactly the same number. Happy with that? Okay? Good. That's hard to get across to younger students sometimes. All right, so then they're just showing you how you do. Okay? One is red and the other is blue. Okay, now this one creates a little issues. Here we go. If 2 cars are selected at random from the car park, what is the probability that one is red and the other is blue? Okay? So we've got an and situation, so automatically we should think multiplication rule, right? Okay? So, now, to select one red car and one blue car, there are 2 outcomes. You can select a red first and then a what? Blue second. Or you could select a blue first and a what? Red second. First, you need to use the multiplication rule. So we just, again, that's easy enough. Just multiply those together. And you're going to get your percent, and you're going to get your number. Red, probability of blue. And then you can use the addition rule to find out if the probability of 2 cars selected are red and blue or blue and red. Because we have this really creates an and or situation. You've got both. Because they both work. So if you find the probability of one, you also have to find the probability of the opposite direction. And this is where it's one of those areas probability starts driving you crazy. Of course you may. Okay? Starts driving people crazy. Okay? So let's go back and look at it so you can see what's happening. To select one red car and one blue car, there are two different ways of doing that, right? Okay? So I would have preferred, and if I was writing it, I would have said, okay, mind, I can get a red, then a blue, or I could get a blue and a red. Now, to me, that makes a lot more sense. Now, what connecting word did they use? I don't like that. Because really, if you're thinking about getting one or another, you wouldn't say and. The way it's just the way they worded it. To select one, there are two outcomes, both this one and that one, right? But if you have two different outcomes, getting two different outcomes is the same as saying this one or that one. Okay? And that's what I'm talking about, the vocabulary, the really reading the directions and understanding what's happening. Okay? This is really an or statement. And you have to be careful. Now, I didn't see this in any of the practice ones that they had done this kind of thing to you, where they gave you something that was just, because if you're on an assessment especially, you see the word and, you're going to think, boom, multiplication rule, right? So I didn't see a place where they did this to you, but you never know, okay? So they probably will do it to you in the homework. If they do it in the examples, they're probably going to do it to the homework. But everybody see that this really is an or statement? You can get this combination or this combination, right? But it's the way they worded it that makes it an and. These are the two combinations, this and this. But it's really an or statement. So C, if you're just reversing this, if you're just reversing the two, that's the same as an or statement, getting this one or that one. Okay? So be careful with the wording. There's really nothing I can do other than to have you have experience to help you with something like this. All right? So it's just going to be experience. So it's really important that you do the homework. Okay? All right. Then it's going into your homework, speaking of that, which means we're done with the lesson, which is good because we're out of time. So here's what I want to do. Don't ever let me get out of here without assigning them, because I'll forget. And I also want to make sure that it's emailing all of you. Yeah, I did that. Yeah. You had any questions?
No, it's a time thing.
Yeah, it's a double period, so I did it. Yeah, I did it. And so I could. Yeah, there's a button I can hit to do multiple periods. That's how I knew it was a double period, because I don't know what I'm doing next time. Okay. All right, so here we go. Assign to your 12 maths. Now, it gives you the whole assignment, and I'll talk about that. But anyway, it gives you 7 days to do it, and then 7 more days, but then it tells you it's late. Do I want you to wait 7 days to do this? Please, no, right? You should have this done before we see each other again. Now, if that's not possible, I understand. It might, but if you don't, okay, then you're not going to know when you have questions, right? And everything that we do builds on what we did before, okay? So make sure you do that. So I'll leave it as the 7 days, but be careful, okay? Doggone it. I lost where I was, so now I got to go back. Okay. Education Perfect is new to me too, so.
That's why
Is it really? Is it good? Is it really good for languages?
Yeah. It's really good if you just randomly want to learn a random language for like a week and then decide
And then not anymore.
I've done that like 4 times.
If you want to do that, though, it's not like
That's the problem. Is it's like, I do
Okay.
great and
Did
then
anybody got your phone? You want to check to see if you just got an email from us from Education Perfect about this assignment? Real quick. I'm sorry. You might. It might take a while. There may be lag time. No. Okay. Thank you so much. Bye. Have a great lunch. Have a great rest of your day.